This video, it's called Introduction to Related Rates. Now, related rates types of problems are just a way in which we can use the derivative. And there's a lot of theory, there's a lot of stuff behind it, but what I'm going to do in this video is to introduce you to this concept. I'm just going to get right into the problem. Okay? And as I'm moving through this problem, I'll explain little pieces here, little pieces there. And tomorrow, when we get back together in class, we'll kind of go over this problem and we'll kind of pull out some general themes and we'll look at a couple more together. So in any event, a related rates equation is basically an equation that involves rates. Okay, so that's kind of what we're talking about here. We're setting up an opportunity to relate rates, things that are varying to other things that are varying. So here's a particular problem. So and this is a pretty basic, famous related rates problem. It's called the sliding ladder problem. So let's assume we have a ladder and it's 10 feet long, right? And it's resting against a wall, at which point the bottom of the ladder starts to slide away, right, at a rate of 1 foot per second. The question for this particular problem is how fast is the top of the ladder moving downward at a particular moment. So at a particular moment when the ladder is 8 feet from the wall. Okay, so a lot of things to consider. First of all, I found a nice website here, GeoGebra, and they created a nice little applet that allows us to visualize what's happening. And so basically what we have here is here's our 10-foot ladder, right? And this ladder is going to slide down the wall. Well, starting here, it's sliding down the wall. Okay? And so essentially we have a right triangle here, right? Can you see that right triangle? And two sides, this piece and this piece, will be changing, right, as the ladder slides down. So if we start here, right, this particular length from the ground to the top of the ladder is pretty large, and the length from the corner of the wall to the bottom of the ladder is pretty small. Okay, and as that ladder slides, first thing to note is that the length of the ladder is always 10, right? So that's not changing. But what is changing is the length from the bottom of the ground to the top of the ladder, and from the corner of the wall to the base of the ladder, right? So those lengths are changing as the ladder slides, right? So in this particular problem, it's called B and A, right? So A in this particular moment is 7.2 and B is 6.94, right? Okay, so that's a situation, and what we're trying to do is figure out how quickly things are changing at a particular moment. Okay, so that's a nice little visual. Let's get back to the problem at hand. Okay, so the ladder's 10 feet, it's resting against a wall, right? At which moment the base slides away. Okay, so the first thing I'm going to do is I'm going to set up, well, I'm going to create another diagram here because I can. There we go. And here's the ladder. And that's 10 feet. And it is at any moment and will always be 10 feet. So these lengths here, A and B, are changing. Okay, as the ladder slides away, the distance here and here will change. So I'm going to call those variables appropriately, so A and B. Okay, but I can feel free to call the length of the ladder 10 because no matter where it's sliding, the ladder is always 10 feet. Okay, so what I can do at first is I can create a particular formula that involves A, B, and 10. And so since I have a right triangle, I can create, using the Pythagorean theorem, A squared plus B squared equals 100. Right, 100 being 10 squared. Right. So I just use the Pythagorean theorem, and I set up a general formula, right, no calculus yet, that kind of could describe part of this situation. Okay. Here's where calculus comes into play. Okay, much like implicit differentiation. Now I'm going to differentiate both sides with respect to t, time. Okay, so watch what happens. I'm going to take, with respect to time, the derivative of both sides of that lame, boring, static Pythagorean theorem. Okay? Now, when you differentiate with respect to time, that imposes rates upon this otherwise kind of static, unchanging Pythagorean theorem. And so by doing just that, differentiating with respect to time, we're kind of bringing this particular formula, Pythagorean theorem in this case, to life. Okay? So I'm going to go ahead and differentiate with respect to t. Now, just like as in implicit differentiation, if you differentiate with respect to t and you're differentiating a non-t variable, you have to use a chain rule. So just like the derivative of y squared with respect to x in implicit differentiation would be 2y times dy dx, Similarly, the derivative with respect to time of a squared is going to be 2a times, by the chain rule, dA dt. Okay. Similarly, the derivative of b squared, b, with respect to t, time, would be 2b times, by the chain rule, dB dt. Okay. And the derivative with respect to time of 100, it doesn't matter what variable I'm differentiating with respect to, its constant is going to be 0. Okay, that right there is my related rates equation. Now, there are a couple rates in this particular equation. Okay, dA dt is the rate at which a is changing. It's the change of a, the length, with respect to time. dB dt is the rate at which this piece b is changing. Right, so those are my two rates. Okay, a and b are lengths in and of themselves, just like we note here on the diagram. Right, but dA dt right here and dB dt are both rates. dA dt is the rate at which basically the top of the ladder is sliding down, the rate at which this length here is changing, and dB dt is the rate at which this length is changing. In other words, the rate at which the bottom is sliding out. Okay, so let's get into this and see if we can use this particular related rates equation to solve this particular problem. Okay, so now what I'm going to do is I'm going to plug numbers in, right? So the problem says, okay, we've got a 10-foot ladder. The bottom of the ladder is sliding at a particular rate, 1 foot per second. Okay, what that means, I'm going to translate to math language. That means that the rate at which b is changing, dB dt, is equal to 1 foot per second, right? The bottom of the ladder is sliding this way, right? So therefore, dB dt, the rate at which b, that distance from the corner to the base of the ladder, will be 1 foot per second. Okay. What I'm looking for is, in this particular problem, is how fast is the top of the ladder? Okay. What's the rate at which the top of the ladder is moving down? Okay. And they ask me to find that, and if dB dt is 1, what I'm really trying to solve for is dA dt, right? That's ultimately what I'm trying to solve for. dA dt represents the rate at which a, that length from the top of the ladder to the bottom of the ground, is changing, okay? Which is the same thing as how the rate at which the top of the ladder is sliding down this wall. Okay. Now it gives me a particular moment. Okay, here's the instant, right? Much like we've been thinking about, well, what's the derivative of this function when x is 2? Or what's the instantaneous rate of change of this function when x is 0? Or what's the slope of the tangent when x is 8? In that light, this is very similar, right? When, so it's at this moment, right? So the moment is when this is happening, right? When the bottom of the ladder is 8 feet from the wall. Okay, so that means when b is 8, right? So in this equation, I'm going to plug in a b, an 8 for b, right? I'm also going to plug in my dB dt, which I know is 1. Okay, and all I need, again, I'm solving for dA dt, right, which is right here, the rate at which the top of the ladder is sliding down. All I need, the only variable that remains, is a. Okay, now if at that moment I know that b is 8, right? At this moment b is 8. So here's my moment, and this is changing, right? So that's why I'm plugging in this value at the very end. So at this moment I'm looking for b is 8, right? So what's a at that moment? Well, by the Pythagorean theorem, a squared plus 8 squared is 100, 10 squared, right? And you might remember that makes a 6, right? That's 6, 8, 10. Okay, so I'm going to take that momentary value and plug that, 6 in for a. Okay, so what I've done is I evaluated numbers, lengths, at this particular moment when the base of the ladder is 8 feet from the wall. In other words, when b is 8, which would require, by this setup, because the hypotenuse is 10, by the Pythagorean, that would make a 6, right? Okay, and also this particular piece here tells me that dB dt, the rate at which, dB dt, the rate at which the ladder is sliding outwards, is 1 foot per second, right? So 1 goes into dB dt, right? That's the rate at which the base is moving out. The base at that moment is 8, so I plug in an 8 for b. dA dt, the rate at which the top of the ladder is sliding down, is what I'm solving for. Okay. At that moment, A, the height, is 6. Okay, so now I'm ready to rumble. I plugged and chugged. Now I just need to solve for dA dt. Right? So it gives me 2 times 6, of course, is 12. That's 16. Bam. I'm going to subtract 16. Divide by 12. So you get negative 16 over 12. Or dA dt is, when I pull a 4 out, I get negative 4/3. And the appropriate label is going to be feet per second. Okay. That's negative 4/3 feet per second. Now, why is it negative? Because it's sliding down, and that length A is decreasing, right? So the rate at which that length A is changing, dA dt, ought to be negative, right? Okay. So this is an introductory, your first problem for the related rates problems, okay? We'll go over some more of these tomorrow. We'll kind of generalize from this particular problem as well. But I did want to share this one particular problem with you tonight as a way to introduce this type of problem. Okay, so come in with questions tomorrow. I'll present kind of a basic process tomorrow as well, answer any questions, and we'll go over together a couple more problems tomorrow in class. Have a good night. Bye-bye.